Okay, so let's get started. Yeah, we've continued our discussion about transactions, right? So we started last week to talk about transaction. Again, this is our motivating example, right? When you are building a real world database systems, it is often the case two things could happen. The first one is multiple users going to have access to your data at exactly the same time, right? You want to make sure your concurrent execution still preserve the same semantic for each user. Right? But on the other hand, each user, each application could also have a group of instructions that they hope to run together, right? So to support both, right, we introduce the notion of transaction. So intuitively, it is simply give you a kind of a notion of a group of instructions, right? So you define that by say, okay, now I begin a transaction, I do a whole bunch of things, then end my transaction, right? So this is actually functionality that we are talking about. So since you start to define the notion of group, right, you can actually try to define the semantics or the property you want for such a group. And we talk about the four of those properties. Atomicity, right, means that each transaction, each one of those group is executed in its entirety or not at all. You will never have the case that you reopen your database, and you'll see, there's a transaction halfway done. That can never happen. Either the transaction is done or transaction never happen, okay? So the second property is called consistency, right? So which means that a transaction, if it runs in its entirety, it's going to bring the database from a consistent state to another consistent state. So here, consistent means that it's going to respect all the integrity constraints. And there's isolation, right? When you have multiple transactions running together, we want to make sure the final result, it is as if the system is running one transaction at a time, okay? So, and then the fourth property is called durability, right? So which means that if you have a transaction that is committed, the system tells the user, okay, I committed this transaction, then the changes caused by that transaction will never lost. Even if the database break down, even if you kind of recover your database, restart your database, the changes will be there, right? The system will not tell the user to say, okay, I know yesterday I committed a transaction for you, but today I changed my mind, I'm going to abort it, right? So that cannot happen. So atomicity, consistency, isolation, and durability. And that is the four properties we want to enforce for transaction. Now we have been talking about how to enforce some of the properties. For example, last lecture on Wednesday, we talked about how can we enforce isolation by doing locking. And we also see a little bit about interaction between isolation and the atomicity and the consistency and durability. If you compare two-phase locking and strong two-phase locking, right, both of them can give you isolation, right? But strict two-phase locking makes it much easier for you to enforce, for example, durability, because that will not have the problem of cascading abort, right? So as you can see, it's a very complex picture. We are going to scratch the surface, right? But in real-world database systems, building a transaction system is actually very complex. So today, let's continue to talk about isolation, right? So last time we talked about locking, but there are more about locking. And we are going to introduce another way of enforced isolation called snapshot isolation. So before we go to the, the new content, let's try to refresh our memory, right? So what is a database in the context of our current discussion, right? It is a set of objects, okay? So we kind of abstract away what is row, what is column, what is table, right? We think about database as a whole bunch of objects with names, A, B, C, D, okay? And each transaction, right, we are also abstract away all the SQL queries, right? We treat each transaction as a sequence of read and write operations. You can read the database object, bring that to a variable A, or you can write it back, okay? So a transaction contains a sequence of those read and write operations. So one assumption that we are making is whenever you are writing something, you have the write instruction, the change is reflected in database immediately, Okay, we also abstract away the buffer manager. Okay. So a new transaction start with begin and can end in two ways. You could either commit or you abort. Okay, so whenever you abort, so that instruction can be issued by two entities. Okay, either by you as a user, or sometimes can be issued by the database. For example, if there's cascading abort, the database is going to abort some other transactions because some transaction aborted. So here's just one example, right? So assuming you have two transactions look like this, right? So you have some integrity constraint. Both we can see, like first we can see both transactions are consistent, right? It's going to bring the database from one consistent state where A equals to B to another consistent state where A equals to B, right? So, and what is the schedule, right? So we keep using this word, what is schedule, right? So schedule is defined as follows, right? When I run these two transactions, right, I can mix the execution of their instructions. I can run the first instruction from T1, then run the second instruction from T2, so on and so forth. Schedule is simply one way of mixing those instructions. There are a whole bunch of serial schedules, right? Which means that I actually, in this schedule, I run the transaction one by one. Here I run T1 first, then run T2, right? If you see how the database is going to change, right? So every single time I write something, I'm going to change the state of my database, right? So, and not all the schedules are serial schedules, right? So actually, we actually want to support schedules that are not serial. So we define the notion of serializable schedule, right? Which is essentially a schedule that can give the same answer as some serial schedule, okay? So for example, you could mix your instruction in this way, right? So there's one schedule. Clearly, this is not a serial schedule, right? Because you are not running the whole thing in a sequential way. However, if you look at the database state, right? So at the end of the day, you are getting the same state as this serial schedule, right? If that happens, we call this schedule serializable. So one thing that we talk about is when you are trying to decide whether a schedule is serializable or not, you are not only looking at the read and write, but you are also looking at the computation itself, right? So we look at one example on Wednesday, that is I can change this computation a little bit, and then I can turn a schedule that's not serializable into a schedule that's serializable. To decide whether a schedule is serializable or not, you need to understand the computation. And that is very hard for a computer to do. So given this, we start to define a stronger notion of serializability called conflict serializability. And the goal is really try to make sure we only decide conflict serializability given the I/O pattern without trying to understand the computation itself. So this is a stronger notion, right? So how do we define it? We start by defining the whole bunch of conflicts between a pair of operations. For example, you have two operations from the same transaction, they're always conflicting, right? So when you have two different operators from two different transactions, O1 from T1, O2 from T2, right? So there's a conflict between them if one of them is the write operation to the same location, right? So there's a read-write conflict, the write-read, the write-write, right? So and we say a schedule is conflict serializable if you can translate the schedule into a serial schedule with a sequence of non-conflicting swipes of adjacent actions. So we talk about all of these three different types of conflicts, right? So we kind of define the notion of conflict equivalence and what do we mean by conflict serializable, right? So at the end of the day, so this is the process, right? So if you say, so I want to see whether the transaction on, the schedule on the left-hand side, whether it's conflict serializable or not, right? So what should I do, right? Yeah, I can take one pair of the operations. Here you have read A from T2, read B from T1, right? So there's no conflict, so I can actually swipe them, right, to get a schedule look like the one on the right-hand side. So these two are conflict equivalent, right? Because you can reach one from the other by a whole bunch of non-conflicting swipe of adjacent operations. And you can keep doing this. You can find another pair of operator that are not conflict with each other, right? You keep doing this, then will lead to the serial schedule on the right-hand side. If you are able to do it, we say the schedule on the left-hand side is conflict serializable, okay? So of course, there are easier ways for you to do it, right? So we talk about how to define dependency graph, right? So essentially you take all the pairs of conflicting operations, right, in your system, and then if, for example, if you take one pair, the write A, read A, in this one, the operation in T1 happened earlier, right? Then you add one edge in dependency graph pointing to T2 from T1, right? So on and so forth. And then you try to see whether there's a loop, right? So if there's a loop, it means that the schedule is not conflict serializable. If there's no loop in the graph, it means that it's serializable. So it means that it's conflict serializable. So this is just a very quick walkthrough about like transactions, right? About different properties, about the notion of conflict serializable, like a conflict serializability. And then we talk about how to enforce it, right? So essentially what's going to happen is in database, there's something called a scheduler, right? So given multiple concurrent transactions, the scheduler makes sure the execution will lead to something that is conflict serializable. So there are two different ways to enforce isolation, okay? So you can take the pessimistic view, meaning that I assume if I do nothing, I will have a whole bunch of conflicts, okay? So under that circumstance, the best way to enforce isolation is before your transaction do anything, you need to ask me for the permission to do that, okay? And last time we talked about one way to enforce it, that's via lock-in. Another view is being optimistic, right? You say, okay, even if I do nothing, highly likely you are fine, okay? Maybe every once in a while you have one transaction that cause conflict, but that's very rare, okay? So if that is the case, right, enforcing lock-in is actually could be very expensive, right? So if you take the optimistic view, you can say, okay, let's let all the transactions do whatever they want to do, but before you commit, you check with me. If you are not introducing conflict, you're fine, I'm going to allow you to commit. Otherwise, I'm going to roll you back, try again, right? So because conflict is very rare in my assumption, rolling back transactions should also be rare, right? So this is a very two different viewpoint about how to enforce isolation because of your different assumptions on your workload. And last time we started from lock-in, right? So it's a very simple thing, right? So the idea is that before the system accesses data X, it need to hold the lock on that. But this thing like itself is not complete because there are two fundamental questions that we need to understand. The first one is when should you acquire the lock? And second is when should you release the lock? So this is just one example, right? So in this example, at the beginning, right? So T1 want to acquire the lock on object A, right? In this case, going to talk to the lock manager. Lock manager going to say, so yeah, no one's holding lock on A. Here's your lock, right? And then T1 can do whatever it wants on A, right? So, and then for T2, they say, okay, I also want lock from A, talk to a lock manager going to say, okay, I mean, T1 is holding that lock, you wait, okay? So then T2 going to wait, and T1 going to do operations on A, and when it's done, it's going to unlock it, then T2 get the lock and continue to do things, and release lock and false commit, right? So this is just one example about how transactions interacting with the lock manager in this course, okay? The real system is going to be more complex, but in this course, this is our mentality model about what lock manager is going to do. So of course, right? So we get back to that two fundamental questions about when to acquire locks and when to release locks, right? So one strategy is called two-phase lock-in, right? So which essentially partition the transaction into two different phases. In the first phase is a growing phase, meaning that each transaction requires the lock that it needs from the lock manager, but it cannot release locks. It can only acquire lock, but cannot release locks. So in the second phase is the shrinking phase, meaning that the transaction can only release locks, but it cannot request new lock from the lock manager. If you look at a number of locks that each transaction hold over time, right? You can see in the growing phase, you monotonically increase the number of locks you have. In the shrinking phase, you monotonically decrease the number of locks you have. Okay. So, and we also talk about a different strategy called the strict two-phase locking, right? It's kind of slightly different from two-phase locking, right? So it partitions the transaction again into two different phases. In the first phase is a growing phase, right? You can request lock in the first phase. However, different from two-phase locking is I kind of require you as a transaction to hold all the locks until the end of the transaction. Okay, you will not have kind of the window between releasing a lock to either commit or abort. Okay, at the end of the transaction, I'm holding all my locks until that time point. I can release all my locks. Okay, if you look at the number of locks over time, right? So you have the growing phase with the number of locks increase monotonically, and then that doesn't change until the end of the transaction, you release everything. Okay, if you do that, that's a strategy called strict two-phase locking. So if you look at them side by side, right? So what's the difference? So we talked about the one difference last time, right? Because you are doing, when we are doing two-phase locking, there could be a problem called cascading abort, like in the sense that, I mean, there could be something happening in the window between you release the lock and the end of the transaction, right? So because of that, aborting one transaction can also force other transaction and maybe even committed transaction to abort, right? And that's not something that we want. I mean, it's going to enforce isolation, right? But going to make it very difficult to enforce other properties. And that is why in many systems, we actually do strict kind of two-phase locking. So now let's start the new content, right? So we still have some leftover about locking, right? So let's finish that. So there are still two questions that we need to understand in locking. Okay, we talk about different type of locks, we talk about locking strategies, we talk about how to deal with deadlocks, but there are two more things that are kind of interesting. First one is the granularity of locks. Because so far we are treating the database as a whole bunch of objects, right? But in reality, right, database is a complex system. You have table, each table have row, and each row has column attribute, something like that, right? So there's a different granularity of objects inside database. How can we accommodate that by introducing the granularity for locks? So that is one question we want to understand. So the second question that we want to understand is there are different isolation levels, right? So we are going to look a little bit about what to do there. Okay, granularity of locks. So let's look at two motivating examples to really motivate us, okay? So here's problem number one. So if you look at these two transactions, right? So you have T1, you have T2, right? And for T1, right, you insert some tuples into this table, right? And for T2, you are actually running essentially two aggregation queries. If you give me these two transactions, right? And then if you enforce locks on tuples, for example, every single time I access a tuple, I acquire the lock. If you do that, what could be the problem? So the problem you have here is that whenever T1 is inserting objects, inserting tuples, right? T2 doesn't hold a lock on those tuples, which means that if you do tuple level locking, I'm going to allow like the following thing to happen, right? So I'm allowing you to do one aggregation on this table, and I still hold all those locks on those tuples, and then T1 insert new tuples, and of course T2 doesn't have lock on those tuples, right? Because it's new tuples, right? And then T1 hold lock on those, do some changes and commit, and T2 acquire the lock from those new tuples, do aggregation, right? So the schedule on the right-hand side could happen if your lock happens at tuple level, right? So, and that could cause problems because this schedule is not serializable, right? Because these two aggregation queries going to give you a different result. right? So this is the problem of Fenton tuples, right? So if you are holding a tuple level lock only, so this problem could happen. So this is actually another problem, right? So we don't care what T1 do, right? Let's look at T2, right? T2 had like a contains query that touches every single tuple in this table. So if you are doing tuple level locking, right? So you actually need to hold lock for every single tuple in this relation, right? Assuming the cons table has billions of tuples, you are going to have billions of small locks, right? So clearly that's going to be very, very inefficient. In the meantime, all T2 want to do is to update the whole table, right? So why don't you give me the lock of that table? Why do you force me to lock individual tuples when you know I need to touch every single one of those? So this is the second problem, right? So, and that means that whenever you are thinking about granularity of locks, right? So you can, I mean, you need to think about the locks on tuples, right? You also need to think about the lock on tables, right? Or other granularity, maybe lock on databases. So that is clearly needed in practice, right? To either enforce the correctness, as we saw in problem number 1, or also improve the efficiency, as we see in this example. So database has a very natural hierarchical structure, right? So this is just one example. At the root, you have a database, you have the whole database, right? Then you have different table. Each table have different tuple. Each tuple has a collection of attributes, right? So database has this very natural hierarchical structure. Whenever we are designing our lock manager, we also want to support locks at multiple granularity, both for correctness and for performance. So how can we do that? So the problem is actually pretty complex. Let's consider a very naive strategy, okay? Which will be wrong. So here's a strategy. Each object is lockable in the sense that I allow you as a transaction to acquire locks on database. If I acquire locks on database, I'm going to put a lock on the database object, okay? And you can also acquire locks on tuples, whatever. And different transactions just lock those objects as they want, as if they were locking tuples, right? In two-phase locking or strict two-phase locking. If you do this strategy, what could be a problem? So now let's look at one example here, right? So here, assuming I have two transactions, T1 and T2. So just for illustration, so T1 going to have a lock that has a color yellow, right? T2 going to have the black lock, okay? And then T2 want to lock tuple 1. Database say, okay, great. Yeah, I'll give you the lock for T2. And then T1 say, okay, I want to lock table 1, right? Under that naive strategy, you are going to give T1 that lock. But clearly that shouldn't happen because when T1 have locks on table 1, the expectation that T1 has is it's going to do whatever it wants on everything related to that table. However, T2 is holding a lock on tuple 1, right? T2's expectation is I can do whatever I want on tuple 1, right? No one's going to touch that. But as you can see, there's a certain conflict, right? Because of this hierarchy. Because when I gave T1 the lock on table 1, I shouldn't give T2 the lock on tuple 1, right? Because tuple 1 is part of table 1. So that is actually what makes the things a little bit complex. That is whenever I'm having different granularity of locking, so those locks are not independent to each other. We need to check whether I really, whenever I'm locking table 1, I need to check whether there exist other transactions holding locks on all the tuples in this table, right? How can we do that efficiently? And that is a fundamental question here. So now let's consider another naive strategy, okay? Before you grant T1 locks, okay, on the whole table, you probe all the leaf node and see whether there are locks. Yeah. So for example, right? So in this case, when T2 try to lock tuple 1, I give the lock. And then when T1 say, okay, now I want to lock table 1. So what's going to happen before I give you that, I'm going to essentially probe all the leaf objects, right? I'm going to say, like, do you have lock here? Do you have lock here? I'm going to enumerate all the leaf node. And then I'm going to say, actually, I cannot give you this lock because some other transactions is holding the lock on tuple 1. So I'm going to ask you to wait. So what's the problem of this one, right? So the good thing about this, yeah, it's going to give you something correct, right? It won't introduce conflict. And this one going to give you something right. The downside is whenever you are having billions of tuples in the same table, we actually do not want to enumerate all those billions of tuples simply because some transaction want to hold the lock on the whole table. It's going to be very slow. Okay? So what can we do? So let me introduce kind of like a simple strategy. It's not it's simple but not trivial, right? So this is what people do in maybe 1970s, 1980s, right? If you look at the real database system today, it's going to be more complex than that. But this gives you the high-level idea about what people want to do. So essentially, the high-level idea is to introduce 3 new type of logs. Okay, so there's one type of log called intention share log, IS log. There's which means that if I'm holding this log, for example, on table 1, okay, it means that some lower node are in the shared mode. Okay, so and I have another type of logs, intention exclusive log. If, for example, table 1 has this log, it means that some lower node are in exclusive mode. And then I have the shared and the intention exclusive, right? If I hold this lock on table 1, it means that I'm actually locking table 1 in shared mode. On the other hand, there's some lower node that I have exclusive lock on. Okay, so this is actually try to introduce, try to give database some way to know the relationship across different layers, right? So when the system want to lock something, for example, if the transaction want to lock tuple 1 in shared mode, it's going to start from the root, okay? It's try to acquire intention share lock on the database level. It means that, okay, I want to do something on this database. I want to hold the shared lock on something in the lower level. Okay, to do that, I start from the root. I first try to get a intention shared lock on the database. If I got it, I'm going to ask intention shared lock on table 1. If I got it, I'm going to acquire the share lock on tuple 1. Okay, so essentially we introduce these 3 different types of new logs. And then whenever I'm trying to acquire a log on something, I'm going to start from the root and first try to acquire intention log. If I get it, I'm going to go 1 level down, have the intention log. I keep doing that until I reach the real object, and then I just acquire the log. So because now we introduce a whole bunch of new logs, right? We have intention shared, intention exclusive, we have shared, right? We have like intention and exclusive, right? And we have exclusive. So the compatibility table is going to change, right? So this is actually compatibility table. But let's look at some examples, right? So and then it's become very simple about how to think about it. So let's look at this, right? So assuming at some node, I'm trying to acquire intention share lock, but in the meantime, there's some other transactions holding exclusive lock. Okay, So assuming, let's for example, table 1, right? Some transactions is holding exclusive lock, but I, as a transaction, want to acquire an intention shared lock. Should the database allow this to happen? In this case, no, of course not, right? Because so only reason I'm acquiring intention shared lock on table 1 is because I want to have shared lock on some tuples, right? Otherwise, I wouldn't want intention shared lock here, right? So I want to have shared lock on some of the tuple in this table. On the other hand, there's some other transactions holding exclusive lock, meaning that that transaction inherently can do whatever it wants on every single tuple below this table, like within this table. So in that case, I will have conflict on some of the tuples. I don't know what tuple it is because when I acquire intention share, like intention share lock, I don't know which tuple I want to lock, right? I mean, at least the lock manager doesn't know. But lock manager knows you want to have share lock on something I cannot give you because I have a transaction locking the whole table, right? So in this case, I'm going to ask you to wait. I will not give you this intention share lock, okay? So now let's look at another example. Let's look at this cell, right? So assuming there's some transactions holding intention exclusive lock here, and then me as a transaction want to acquire a share lock on this. Will the database give me that? Right? So the way of thinking is very similar, right? So what do I mean by having a share lock on this table, right? It means that for every single tuple of every single attribute within this table, I want to have share lock, right? So I want to read every single one of those. Whenever you have intention exclusive lock from some other transactions, it means that that transaction, although that transaction won't change all the tuples in this table, it is holding exclusive lock on some tuples in this table, right? In this case, there's no way I can successfully acquire a share lock on all the tuples because someone else is holding the exclusive lock on some of them, maybe not all of them, but only some of them. But even that is enough to say you cannot have share lock on the whole table, right? So in this case, if you do this, database is going to say no to you, right? Now let's look at some example, right? So assuming you have two transactions, you have T1 and you have T2, okay? And then assuming T1 want to have a share lock on tuple 1 and T2 want to have exclusive lock on tuple 2. So what would happen, right? So assuming that T1 issues the request first, so what's going to happen is it's going to start from the root because it wants shared lock on tuple 1, right? You are going to have an intention share lock on database. If the database gave it, it's going to go down one level, try to have the intention share lock on table 1, right? If it get it, then it's going to have the share lock on tuple 1. In the meantime, T2 is also going to start from the root, right? Because it wants exclusive lock on tuple 2, right? It's going to try to ask database, okay, can I get intention exclusive lock on my database, right? And in this case, the database is going to be fine, right? So I mean, you guys want to deal with the same database, right? I mean, there's a one intention share lock, there's one intention exclusive lock, right? It is entirely possible you are going to deal with different objects, right? I'm going to give you that, right? And also you can actually look at this compatibility table, right? You can say, I already have IS lock. Can I have a IX lock? Yeah, yes, right? That makes sense, right? And then transaction 2 going to have it, and then it's go down one level to say, okay, so I also want intention exclusive lock on table 1, right? So here is also okay, right? And then T2 going to go down to say, okay, I want to have exclusive lock on tuple 2, okay? And that's also okay because transaction 1 is holding lock on tuple 1, not tuple 2, right? So this is what's going to happen when you have multiple transactions. They are actually try to lock tuples when you really expose them to the hierarchy inside your database, okay? It's going to acquire intention locks for all the upper layer objects until it issues the real lock on the object you want to lock. Okay. So now let's look at another example, right? Assuming T1 want to have a share lock on table 1, and T2 want to have a share lock on tuple 2. Okay, so what would happen? In this case, again, right, T1 is going to have intention share lock on database, assuming that succeed, then it's going to actually have share lock on table 1, right? And then you have T2 going to try to say, okay, I want to have intention share lock on database, I'm getting it, right? And then I want to have intention share lock on table 1. In this case, also fine, right? So share lock is compatible to intention share lock, right? For obvious reason, right? So, and then it's going to go down one level to say, now give me the share lock on tuple 2. Yeah, the database is going to be fine with that. So as you can see, right? So this is actually a very simple strategy, but you can see the complexity, right? So if you are the first one trying to develop such a thing, well, I mean, at least for me, I can imagine myself making a lot of mistakes, right, in designing such a thing if I don't know the answer, right? But once you know the answer, and it's pretty natural and simple, right? Okay. So this is about the granularity of locks. So another thing that we can talk about is different isolation levels, right? And we talked about that last week on Friday, right? So you can have serializable schedules, but you can also make them weaker, right? For example, you can have read and committed, right? Non-repeatable read, so on and so forth. They are actually weaker than the fully serializable schedule. If you are doing two-phase locking or strict two-phase locking, you can actually twist the protocol to implement different isolation levels that's supported by the SQL standard. Okay, so like just recall that the different kind of like isolation levels, right? So you have read and committed, you have like read committed, you have repeatable read, you have serializable, right? On the other hand, each of them could give you different anomalies, right? If you are doing read and committed level, right, you could even have dirty read, right? So if you are doing kind of repeatable read, you could have different like phantom tuples as we saw, right? So like all the way from the bottom to the top, right? You are faster, meaning that you are allowing more type of schedules, but on the other hand, you could have more anomalies. So how can you twist that, right? So essentially, it's by twisting what type of locks that I need to hold before I can do something. Okay, so when if you want to enforce serializability, right? Essentially, before I read, before I write, I need to have the corresponding lock. If I want to read something, I must have share lock. If I want to write something, I must have exclusive lock. Okay, so if you do that, it's going to give you a fully serializable schedule. So if you do, but that's not enough for serializability, right? Because like we saw it, you actually need to hold locks on the table, right? So that's called index lock, right? Whenever you have that, it means that like other transactions cannot insert new tuples, right, into the same table, right? So like essentially, if you really want to have full serializability, you need to have the notion of granularity, right? So I need to be able to hold locks on the whole table, right? Meaning that I need locks on all the future objects that you could insert into that, right? If you do this, you have fully serializable schedule. If you simply do strict two-phase locking on tuples, right? So that's going to give you essentially a repeatable read, right? So, and if you say, okay, here's my strategy. I ask you to have share lock and exclusive lock, right? But I'm going to release my share lock immediately after I read it. Okay, if you do this, you are going to enforce the isolation level read committed. Okay, and then if you say, okay, so you do not need share lock at all. I mean, when you write something, try to hold the exclusive lock, but when you read something, you don't need lock. Okay, if you don't have that, you are actually in the level of read uncommitted, right? You could read uncommitted like values, right? Because someone else may hold in the exclusive lock. You don't care. You just keep reading it, right? So you are reading uncommitted values potentially. So essentially, you can actually twist the strict two-phase locking protocol to really support like each one of this, right? And that's actually very interesting. So all of this, actually, we actually spent almost two lectures talk about this. This is actually in the really, really fundamental paper by Jim Gray, like maybe 40 years ago, right? So if you are curious about this, you can try to read the paper and you can actually see how beautiful the whole thing is, right? So think about people are doing this research like 40 years ago without knowing the answer, right? Okay, so we are not going to do this live demonstration, right? So, but if you want to kind of play this database to see how that really works, right? So, I mean, especially you want to understand locking, right? So the default setting in MySQL is actually using locks, okay? So if you just do PostgreSQL, you are going to see a different behavior because by default it's using snapshot isolation, the thing that we are going to talk about in the second half of this lecture, right? If you want to play with locks, if you want to see those transactions wait for each other, right? So you might need to use MySQL, right? So the way to do it is you can actually open the same database, two like two different like connections, okay, and you run them side by side, okay. So like this is just to give you some example, right? So for example, in the first repo, you first run like this instruction, and then the second one you run this, run this, run this, okay. So if you do this, you can actually see how those transactions wait for each other, okay. Try to verify your understanding about how locking works and also how different isolation level works. Okay, so we are not going to do that today, right? During the lecture, but when you go back home, just if you want, right? So just install MySQL. Yeah, make sure it's not PostgreSQL because you are going to see a very confusing behavior, right? If you do that, and you are going to understand why in the second half of the lecture. Yeah, otherwise you just go back home and play with it, right? So I actually put multiple example here. Just one example, right? So like this another different examples. Yeah. So I put 4 examples, and you can see when does these two transactions in different windows, okay, going to wait for each other. Okay, so that's actually something very interesting to see. Okay, so this is the first half of the lecture, right? So we finished up what we left about locking, right? We talked about granularity of lock-ins. We talk a little bit about how to enforce the high-level intuition about how to enforce different isolation levels. So in the second half of the lecture, we are going to talk about how to take a more optimistic viewpoint. If you assume all those conflicts between transactions are very rare, right? So how can you enforce that? We are going to talk about different strategies of enforcing isolation beyond using locks. Okay, so let's take a break. When we get back, we are going to talk about that. Otherwise, if you have any questions, just speed up, and I will be here to answer the questions. Yeah. Okay, so let's continue. Yeah, now let's try to talk about how to enforce isolations, not by locking, but some other mechanism. Okay, so the first way to deal with concurrency control, right? So in an optimistic way, right? So which is not what PostgreSQL is doing, as we'll see, it's by using timestamps, right? So the intuition is actually very simple. That is, our goal is to guarantee serializability, right? So that is whatever schedule that I'm allowing, right? So I need to enforce a serial order of execution of transaction running concurrently. Okay, so assuming non-serializable behavior is very, very rare, in the sense that maybe like after like 10,000 transactions, you have one transaction just conflict with everyone else, right? So, but otherwise, all those transactions, they play nicely with each other anyway, right? If that is the case, one thing we could do is you say, okay, I mean, you want to enforce a serial order? Fine. I'm going to predefine a serial order, okay? For example, I can say, okay, it's first come serve, like it kind of first come first serve, right? I mean, if T1 start earlier before T2, in my serial schedule, I always want T1 happen before T2, right? Whatever schedule I'm trying to enforce, it must has T1 then T2, okay? So I predefine a serial schedule, and whenever there's some transaction break this order, for example, it's reading from the future. For example, I'm trying to enforce T1 and T2, and then now T1 try to read the result from T2, right? I roll back T1, right? So that could be a very, very simple strategy, right? So I predefine a serial order, and whenever you read and write and check whether you are breaking this serial order or not, if you are breaking it, I roll you back, okay? And hopefully, because I'm being optimistic, hopefully this type of behavior, the rolling back of all the transactions, will be very, very rare. And then I have a system that can have a very high throughput, but I can also enforce serializability. Okay, so that is the whole. We can make this intuition a little bit more concrete. So here's a basic idea. So for each transaction, I assign a timestamp. Okay, so and I call that TS. Okay, for TSTI means that's a timestamp of transaction TI. If the timestamp of TI is smaller than timestamp of TJ, it actually means that actually TI happens like TI being, for example, being submitted before TJ. Okay, then my database must ensure the execution schedule is equivalent to a serial schedule where TI appears before TJ. Okay, so given the timestamp, essentially you can compare timestamps, right? So you actually define a serial schedule, and I want all my execution to be equivalent to that. And we can make this a little bit more concrete. So there are two fundamental questions. The first one is how should we assign timestamps to a transaction? So here you can do whatever you want, right? I mean, as long as you, for every single transaction, you have a unique timestamp, I'm happy, right? So you can use system lock whenever, like system clock, right? Whenever you are submitting a transaction, I just read my clock. I say, okay, so this is your timestamp, right? And for next transaction being submitted, I give you a different timestamp. So you can have some logical counter. So this is the 20th transaction. That's the 21st transaction, right? I can also use that as timestamp, right? So as long as it's monotonically increasing, it's unique for each transaction, I'm happy, okay? So every single transaction has a timestamp. And each database object is also associated with a timestamp. So there is the read time of object X. It is the highest timestamp of a transaction that has read X. Okay, so whenever a transaction read X, we actually take note about the timestamp of that transaction, and I take the max. And I take the max as the read time of X, like this object. And then there is also the write time of X. right? So that's the highest timestamp of transaction that has written X, right? Whenever I have one transaction, I try to write to X, right? I keep note of the timestamp of that transaction. I take the max, and that's my write time for that object. So here's the protocol, right? So we now know every single transaction has a timestamp. We know the high-level idea, right? So we want to enforce a serial schedule, kind of that's consistent with your timestamp, right? And for each database object, I have read time and I have write time. So here's the protocol. So each transaction read and write objects without locks. Okay, I don't hold lock. I just keep reading and writing. And each object is tagged with a timestamp of the last transaction that successfully read and write. Okay, so this is essentially you update your read time and write time of that object. If you have a transaction TI that try to access an object from the future, meaning that, for example, it try to read an object X, but X is written by a transaction with a larger timestamp, right? Meaning that this transaction TI is actually read from a future transaction, right? So that's going to break my serial order. If that happens, I'll abort and restart TI. So this is just a very simple protocol. But as you can see, as long as you enforce this protocol, you are always going to enforce a serial schedule that is consistent with the timestamp, because your transaction will never read and write from the future, right? It can only update all the changes that have been reflected by the transaction happen in the past. Here, past is defined by the timestamp, right? So as long as you follow this protocol, you are going to have a schedule that is serializable. And it is serializable because you are actually enforcing that to be equivalent to one predefined serial schedule, okay? So now let's look at like some more small things, right? So imagine you have a transaction TI. Assuming TI want to read X, okay? And X has a write time. And assuming the timestamp of TI is smaller than the write time of X. In this case, will you roll back TI? Yes, in this case, I'm going to roll it back. Why? Because my X is written by a transaction happen in the future. If I want to enforce the serial schedule, that TI happens before TJ, where TJ is actually the one kind of writing to X, there's no way TI going to have access to the changes enforced by TJ, right? So when I'm trying to read, when I'm trying to read from X, in this case, that cannot happen. It's going to break my serial schedule, right? I'm going to abort TI. So similarly, right, you have TI, and it try to read X, right? And if you look at the write time of X, right, so it's actually happened in the past, right? The timestamp of TI is larger than the write time of X. In this case, what I'm going to do? Yeah, in this case, it's fun, right? So X was updated by a transaction that's supposed to happen in the past because it has a smaller timestamp as I'm TI, okay? And then in this case, I'm fine, right? I'm reading from the past, right? So I just allow TI to read X, and then I update the read time of X, right, to the max of the timestamp of TI and also the current read time of X. Okay, I just update the read time. So imagine you have TI and try to write to X with a write time that happens in the future, right? In the sense that the timestamp of TI is smaller than the write time of X. In this case, of course, it cannot happen because I'm trying to overwrite an object in the future, right? So that cannot happen. That's going to break my serial schedule. I'm going to abort TI. Okay. So otherwise, right, in other cases, like for example, if the timestamp of TI is larger than the timestamp, the write time of X, right? So I'm going to allow TI to write to X, and then I'm going to update the write time of X. So in the last case, right, so imagine you have TI, you want to write to X, and then X has a read time happen in the future, right? So clearly this also cannot happen, right? What should you do? You abort TI, you restart, right? Otherwise, you just allow TI to write to X and you update the write time. So as we can see, this is the 4 cases that could happen in the systems, right? So as long as I'm read and write on an object that has been accessed in the future by a transaction that's supposed to happen after me in the serial schedule, I will abort TI. Okay, so that's a high-level principle. And as you can see, as long as you follow this protocol, you are going to have a serial schedule, right? And if all your transactions are going to happen like running concurrently very nicely with each other, they access different part of the database, right? So it's going to be very, very fast because you do not need to hold lock. And if you are really right to be optimistic, it is very rare that you need to roll back a transaction, right? So that's a beauty of optimistic concurrency control, right? When you are right to be optimistic, you can make the system much, much faster. So now let's look at 2 concrete examples. Assuming I have 2 transactions, T1 and T2, okay? And in this case, right, assuming the user just submit T1 before T2, so T1 get lucky, right? So timestamp of T1 is 1, timestamp of T2 is 2, okay? So then what's going to happen is I will try to enforce the serial schedule in which T1 happened before T2, okay? That's it. From that, like that's my principle. And then let's try to follow this. Assuming I have 2 objects, I have A and B, okay? I have the read time of A, write time of A, read time of B, write time of B, okay? I'm going to trace these 4 values. At the beginning, they all have 0, for example. And then T1 try to read B. So what would happen, right? In this case, T1 have timestamp equals to 1, is try to check, okay, can I read B, right? It's going to check the read time and write time of B, both are 0, right? So that they're in the past, right? No future transactions have accessed that. I'm okay, right? So I'm going to allow T1 to read B, and then I'm going to essentially update the read time of B, right? So here the read time of B become 1 because the latest transaction, the highest timestamp of a transaction reading B is T1 now, right? So it's 1. And then T2 start. T2 try to read B. Do we allow that to happen, right? In this case, right, so T2 had timestamp equal to 2. It's going to check the timestamp of, the read time and write time of B, right? In this case, you say, okay, so the read time of B, the last time B was read by some transaction, that transaction was T1. I supposed to happen after that. So I'm fine. I can read something that has been read by T1, right? If I look at the write time of B, yeah, no transaction have ever updated, right? So yeah, it's fine. I'm going to allow T2 to read B, and then I'm going to update the read time of B. And then T2 want to write to B. Do we allow that to happen? In this case, again, I'm going to check the read time. I'm going to check the write time. In this case, no future transactions has read or write to B. Yeah, I'm fine. In the current serial schedule, and that could happen, right? So then I write to B, and then I also need to update the write time of B because now I write to B, the highest timestamp transaction that write to B equals to 2 now, right? And then assuming T1 say, okay, I want to read A, can you allow that to happen, right? Yeah, so I check the read time and write time of A, right? And I update the read time. And then if T2 want to read A, I'm also fine. T2 want to write to A, I'm also fine, and both commit. So as you can see, this is a serial schedule, right? And if you think about the execution, it's going to be very fast because there's no lock-in. No one waits for each other, right? So that's actually the beauty of optimistic concurrency control. So now let's look at one example here. Okay, it's getting a little bit tricky. Again, two objects. So I am interested in the evolution of these four numbers. At the beginning, it's all 0. And then T1 read B. Okay, yeah, that's fine. I'm going to update the read time of B. And then T2 start. T2 read B, of course, it's okay, right? I update it. T2 write to B, I'm okay. Now it's become interesting when T1 want to write to B. Do we allow that to happen? In this case, if T1 want to write to B, I'm going to check the read time and write time of B. In this case, I will say, okay, I'm T1, I have timestamp equals to 1. But there are some transactions with timestamp larger than me, have already read B and also write to B, right? If I write to B, I'm going to overwrite an object that has been accessed by a future transaction. That cannot happen. That cannot happen in a serial schedule where I happen before that transaction. Where T1 happens before T2, if you have that serial schedule, this type of overwriting will never happen, right? So I want to write B, but I need to overwrite the future. There's nothing I can do. System is going to deny it and roll back T1. Okay, because T1 try to touch the future. We don't like that, abort. Okay, and then T2 continue. T2 do whatever it wants, commit at the end, right? T2 can commit. So this is just another example that there are just type of conflict, right? In this case, you are going to abort T1. So what guarantee can we have here, right? So it's going to give you a schedule, right? So that's confidence realizable. If you think about why, because you never read and write to the future, right? So if you imagine the dependency graph, all the edges are from the past to the future. It's never go back, okay? So there's no deadlocks. Why? Because transactions never wait for each other, right? They just do whatever they want. I mean, if they break the dependency, they abort, okay? What could be the potential problems, right? So I think now, like we are toward the end of the semester, as you can see, every single time we talk about some solution, there are potential problems. That's the interesting part of building a system, right? There's no perfect solution. There's no free lunch. What could be the potential problem of concurrency control using timestamps? Well, there are a lot of things. First one, if you are optimistic when you shouldn't be, right? So the performance could suffer, right? If all those transactions, they have conflict with each other all the time, but you are optimistic for some reason, you believe there's no conflict, you believe the conflict is very rare, but in practice, conflict happens all the time. Concurrency control with timestamp could be very, very slow because you are keep rolling back transactions. At the end of the day, if there are a lot of conflict, no one can make any progress. You end up kind of rolling back all of those transactions, right? So if that happens, if you are wrong to be optimistic, but you are being optimistic, the performance could suffer, right? Under the right assumption, this is a very good strategy. But if your assumption is wrong, this could suffer. And another problem, right, is there could be a problem called starvation, right? So let's look at this example, right? So I have 4 transactions. I have T1, T2, T3, T4. The difference is T1 is a very long transaction. It's going to run for a while, look at so many different objects, right? So T1 is very long. T2, T3, T4 are very, very short transactions. Okay, they touch some object, commit, touch some object, commit. In this case, you are actually not being fair to the long transaction, right? Because the probability that rolling back T1 is much, much higher than the probability that you are going to roll back T2, T3, T4, right? If you have a very long transaction and all the other transactions keep having those kind of smaller transactions, but you have one long transaction, you are going to keep rolling back T1 at the end. Okay, so we call that the T1 actually starve to death, like because it will never get executed. It's like whenever I want to run it, there's some future transaction access my result, I need to roll back, and then I restart, I run for a while, there's another small transaction coming in, screw it up, and then I need to roll back, right? I submit the T1, but never get finished. Okay, so that could happen if you are doing concurrency control with timestamps, right? So like in practice, you really want to do this, you really need to keep track, like how many times that you are rolling back one transaction. If that number becomes too large, you need to intervene and use whatever strategy to make sure you don't starve a transaction to death. Okay. So another problem, right, is cascading abort, right? So whenever you are dealing with concurrency control with timestamps, this could also be a problem, right? So concurrency control is all about isolation, right? But it's also interact with the other properties that we want to enforce, for example, durability. So let's look at this example, right? So assume you have T1 and T2, and T1 happened before T2. Now, T1 has timestamp 1, T2 has timestamp 2, right? So, and we try to understand the evolution of these four numbers, two objects. At the beginning, T1 want to write to B. Yeah, I'm fine, right? So I allow it. I'm going to update the write time of B to 1, because that's my timestamp of T1. And then T2 start. It try to read B. In this case, of course, you can read B, right? So B has been updated by T1, which is in the past, right? So yeah, allow it. And then T2 try to write to B. Yeah, sure. Yeah, why not, right? So, sorry. Yeah, T2 try to write to A. Yeah, again, why not, right? So I do it. I update it. And then T2 commit. In this case, do we allow the T2 to commit? Yes, your protocol, you can commit. You can commit whenever you want, right? There's no conflict, right? Then T2 commit. And then you imagine at this time, T1 abort. Then what do you need to do? I need to roll back T2. Why? Because T2 have been using the value of B written by T1. But I want to roll back T1. T1 never happened. So I need to roll back T2 too. But T2 has already been committed. What can I do? Right? If I want to enforce durability, there's nothing I can do. I failed. So that's a problem of cascading abort if you want to do concurrency control with timestamps, right? So essentially the protocol that we have been talking about is not really enough in practice. So in a textbook, 1883, right? So you can see, you can actually twist the protocol slightly to avoid cascading abort, right? So, and it's kind of easy to understand once you know the principle of how to deal with concurrency controls and timestamps, right? So when you go back home, read that section, right? So then you can see how to avoid cascading abort when you do concurrency control with timestamps. Okay, so this is just a very simple protocol to do optimistic concurrency control, to enforce isolation by assuming that I'm able to do optimistic thing. Now let's talk about another strategy, which is very similar to concurrency control with timestamp. That is something called snapshot isolation. It is very interesting because when you are using PostgreSQL, right, by default, this is actually what happened. Okay, so the idea is also very simple. When a transaction starts, it receives a timestamp. Okay, and again, the high-level idea is every single transaction has a timestamp, and I will try to enforce a serial schedule that is consistent with the timestamp. Okay, transaction with a smaller timestamp in that serial schedule should happen earlier. And then, whenever a transaction starts, I create a snapshot of my database. Okay, I have the parallel universe. all of those transactions, they work in a parallel universe. Okay, T1 works on its snapshot, T2 works on another snapshot. Okay, and then they just do whatever they want to their snapshots, not the real data. Okay, they work on a snapshot. And then when both finished, I try to check how to merge my snapshot back to my original database. And when transaction commits, it checks for conflicts when they try to merge the snapshot back. For example, you have T1 and T2, both of them run concurrently over two different snapshots. Okay, you run them to the end and you try to commit. I'm going to abort T1 if there exists a T2 such that T2 committed after the timestamp of T1, but committed before T1 commits. Essentially, T2 happens, T2 commit after T1 start, but before T1 commit. And if T1 and T2, they updated the same objects. This is very similar to the idea of concurrency control using timestamps, right? If such T2 exists, that is T2 commit after the T1 start, but before T1 commit, right? And then if T2 update the same objects as T1, then essentially T1 is overwriting the future, right? And I cannot allow that to happen, so I abort T1. Okay, so that's a high-level idea. So the benefit of this is, again, read and write do not block each other, right? Both T1 and T2, they work in a different snapshots, and I only merge them back when each transaction finished. So during the execution, no one waits for each other. Okay. In an extreme case, right? So assuming you have a database where all transactions are read-only. Okay, I never update anything, I just keep reading. Oh, I mean, then the snapshot isolation is extremely good, right? So why? Because I will never have any conflicts, right? So, I mean, all the transactions, they work in parallel, right, on their different snapshots. When you merge them back, I always allowed to do that because there's no updates. Everything is read-only, right? In that case, you have extremely efficient systems, right? So, I mean, that's one extreme case, right? But you can see the power of snapshot isolation. But of course, like all the ideas that we talk about in the course, there's no free lunch, right? Whenever you choose to do this type of snapshot isolation, you pay something, right? So, and there could be problems, and we are going to see them soon. Okay, let's try to understand a little bit better about the protocol. Okay, so here, assuming you have two transactions, T1 and T2, they have their corresponding timestamps. 1 and 2, T1 happened before T2, that's what I want. What's going to happen inside the database is you are going to store different versions of your data, okay? Because I have multiple snapshots, right? I mean, yeah, I can store those snapshots independently, right? But I can also keep different versions of the same value, okay? And then in this case, for example, you have your object A, right? Inside my database, right? So I'm going to have different version of A at the very beginning. The value is 100, okay? I also keep the begin and end, right? Which essentially tell my transaction, if I am accessing the data A, right? Which version should I access, right? Begin and end is the begin and end of the timestamp, right? So here the begin 0, end is undefined. It's meaning that if you are transaction with timestamp larger than 0, yeah, you should read this. You should read this version. Okay, you are working on this snapshot, and then you have T1. T1 try to read A. Right? In this case, yeah, I'm going to access version A0, right? So I'm going to get A equals 100. In this case, you have T2 come in. You try to write A. So assuming we try to A equal 200. In this case, okay, so we are going to create a new version of A for T2, okay? Because T2 works on its own snapshot. So the mentality model is whenever T2 start, you copy your whole database and give that copy to T2, and T2 going to do whatever it wants on that copy. Okay, but in reality, we don't want to create the real copy. So we are going to keep different version of A to make sure whenever T1 read and write is going to be on the version A0. When T2 read and write, it's going to be on the version A1. Okay, so T2 want to write. So I create a new version of of the object A, put the value equal to 200, for example, and then I update the beginning and end of each version. Right. So here I actually update the begin and end for A0 to begin 0 and 2, right? Meaning that for all the transactions in between 0 and 2, you should access A0. That's your snapshot. Okay. For all the transactions with the transaction ID larger than 2, you guys deal with A1. That's your snapshot. Okay. So essentially you have two different snapshots, one for T1, one for T2, and then they are going to do whatever they want within their own snapshot. Okay. And then assuming T1 read again, yeah, I should read my own snapshot. I should read A0, I get 100. And then when T2 read again, I'm going to read my own snapshot, right? So I look at the table, I find A1, right? So I'm going to read again, then get 200. So as you can see, this is a very efficient way for you to implement this kind of snapshot isolation type of semantics, right? So instead of really copy the data to create a real snapshot, I keep different versions of the same data object, right? Such that each transaction can deal with different snapshot, right? By just looking up which version I should access. Okay. So now let's look at another example. So in this case, right? So I have these two transactions, right? So when T1 read, I'm going to read version A0. When T1 write, right? So essentially, I'm going to create a new version, right, for T1, right? So and then like when T1 read again, right? So I'm going to read from A1, not A0, right? And then I'm going to update this. And when T2 read, where should T2 read? So think about this. Where should T2 read? In this case, T2 should read A0. Why? Because whenever you are creating the transaction T2, you create a snapshot. And here, because when T2 begin, right? So you haven't updated this yet, right? So when T2 begin, T1 hasn't committed yet. So we want T2 to have access to a database state as if T1 hasn't happened yet. That's snapshot, right? Well, T1, I mean, T1 is doing their updates in their own snapshot. All other transactions don't know, right? When T2 try to read the value, it need to read the value as if T1 hadn't happened. So T2 should read version A0, okay? And then when T2 write, we create essentially a snapshot, right, for T2, right? So then T2 going to work on version A2, T1 going to work on version A1, okay? And then when T2 and then when T1 read, yeah. And then in this case, assuming I want to commit T2, right? So in this case, can I do it, right? So in this case, actually no, right? So you go back to the protocol, right? So when T2 commit, I check, like in this case, it's going to commit after the timestamp of T1, but it's going to be before T1 commit, right? And it's update the same object of T1, right? So in this case, I either abort T1 or abort T2. I can choose to abort T2, right? In this case, if I allow T2 to commit, it means that T1, when it merge back, is going to overwrite the future, right? So that cannot happen, right? I could wait until T1 commit to abort T1, or I can just abort T2, right? So in this case, we can just abort T2, T1 continue, and that's it, right? So this is a very simple thing, right? So once you abort T2, right, when T1 read, it's going to read its own snapshot, right? So in this case, it's going to read version A1, okay? When it commit, it's fine, right? So this is a very simple idea of snapshot isolation. So as you can see, it's actually follow the same principle as concurrency control using kind of timestamps, right? So you predefine a serial schedule and you try to check the conflict when some transaction try to commit, right? But in this case, you are like each transaction work on their own snapshot, right? So, and that's the only difference. So yeah, I don't know why today like Code seems to be down, so I cannot show this real demo. But when you go home, right, you create a relation R inside database, right? So there is kind of a hidden attribute for each of the relation called xmin and xmax, and that is actually the begin and end that we see here. Okay, so when you go back home, open two PostgreSQL connections, put them side by side, and run this in this order. Okay, you start two transactions. Okay, and you can actually select transaction ID, and this one is going to give you the snapshot. Okay, and then you in the first transaction you select this xmin, xmax star from R. Okay, it's going to give you begin, end, and the value. And then in another transaction you do the updates. Okay, and then in the first transaction you do this again, xmin and xmax, and you are going to see the evolution of begin and end. Okay, so for this you are going to see whenever you do the updates, you are going to see the different copy or different version of the data. Okay, so this is something very interesting, but I don't know why I cannot access Code, but yeah, so I cannot show you that for real. But when you go back home, open to PostgreSQL repo, and this is very, very easy to see and actually very interesting, right? So this is actually what database is actually doing, right? So now let's talk more about snapshot isolation, right? So let's look at this example, right? So T1 read, then T2 read write commit, then T1 write commit. So in this case, right, when T1 try to commit, you are going to have problems. Why? Because you are going to abort T1, right? Because in this case, you have a transaction T2, it commits before T1, right? And both of them have conflict on A, right? So in this case, right, so according to the protocol, I'm going to abort T1, right? Because if I do not abort T1, I merge back the write of A, I'm going to overwrite the future, right? Because T2 has a larger timestamp, and I already committed T2, so no one can overwrite, no one in the past can overwrite the result of T2, right? Because T2 is the future, right? So then in this case, I'm going to abort T1, right? So now look at this example, right? T2 start earlier, and then I read A, and T1 read A, right? So in this case, right, so I'm also essentially going to like about T1, yeah, actually for the same reason, right? So here, like it's because for some reason the system give T1 timestamp 1, give T2 timestamp 2, okay? In this case, that's the same. T2 is the future, right? It doesn't matter whether T2 begins, yeah, slightly earlier than T1, it doesn't matter. Always matter is the timestamp the system gave to these two transactions. In this case, the timestamp of T1 is smaller than timestamp of T2. So T1 is the past, T2 is the future. The future committed, I cannot overwrite it. So whenever T1 want to update A and commit, I'm going to abort T1. You cannot overwrite the future. So what if you have this, right? Yeah, this is the same thing, right? So T2 is the future, It's already written. I already merged it back. You're like committed. You want to write? No way. Okay. So how about this? Yeah, of course. Like for this one, right? So like T2 commit before T1 even like started, right? Then of course, right? So I'm fine. Right. So how about this case, right? So yeah, we are going through this really fast, but when you go back home, think about it, it all actually makes sense. Okay. So like in this case, you have T1 read and write A, you have T2 read and write A, and T1 read B, right? And then T1 abort, right? In this case, there's no cascading abort. Why? Because each transaction, they work on their own snapshots. And T1 commit, I throw away the snapshot, right? It has nothing to do with T2, right? So that's the beauty, right? So there's actually no cascading abort in the case of snapshot isolation. And again, so one thing that's very important is this read is not uncommitted read, because this read will not know about this write from T1, but they all work in their own snapshot. This read have no access to this write. Okay, so it's not read uncommitted value. Okay. Okay. So this is another example, right? So T2 is doing some aggregation, then T1 insert tuples, then T2 do another aggregation, right? So this case actually also interesting because there are no Fenton tuples, because both of them are work on their own snapshot, and the snapshot is at a table level. Okay, so whenever T2 start, I'm going to have one snapshot of the whole table. Logically, physically, you keep different versions, right? So T1 also have their own snapshot. They do in parallel. There's no Fenton tuples. Okay, so that's actually the beauty. So the good thing about snapshot isolation is there's no read and write being blocked, right? It's very fast. So the overhead is you need to keep the right side of transaction by creating different version, right? So it's actually very efficient to implement a bot, and sometimes it's not too much overhead to keep all the version of the object, because in database often that is something you need to do anyway, right? So there's no deadlocks, but there could be rollbacks, right? So that's the trade-off. So what's the problem? The problem here is actually very interesting. So there's a problem called red skew, and we are going to look at it, because think about you want to check integrity constraint. When should that happen, right? So in snapshot isolation, at least in our protocol, the integrity constraint is being checked also in the snapshot. But if you think about that, that could cause problems, because it is entirely possible you have two snapshots, the integrity constraint hold in both snapshots, but when you merge them back, they do not hold anymore. So now let's look at one example, okay? So assuming you are building a database for hospital, you want to have you have two doctors. You want to make sure at any time there's at least one doctor in the hospital, okay? And at the beginning, both A and B are on duty, and you have two transactions. T1 going to set A free, say A, you go home. It's going to check the constraint, whether I have at least one doctor, say, okay, B is here, and fine. And then for T2, right, it's going to say, okay, B, you go back home, you are free. It's going to check the constraint to say, A is here, right? So I have one doctor. And then when both commit, because they are dealing with different objects, there's no conflicts, right? So, and then if you commit it back, you have a violation of your constraints, right? Because now both A and B are home now, right? There's no doctor in the hospital anymore, right? Even though your constraint hold within each of those snapshots, we'll merge them back. If you're not being careful, you could have the violation of your constraints. If you think about this, this is actually very interesting, because fundamentally speaking, if snapshot isolation is really trying to enforce serializability, the previous case should never happen, right? Because if it's really serializable, I'm not going to have inconsistency. That actually tells us something very important. That is snapshot isolation, as good as it looks like, at least in the current protocol, does not enforce serializability. And this is a very concrete example. We'll go back home, read this example, and you can see why snapshot isolation does not necessarily enforce serializability. Okay, so that is actually very interesting. So like you can see that statement just by looking at this example, right? If you really enforce serializability, this should not happen at all, right? Because every single transaction brings the database from a consistent state to another consistent state. If you are really serializable, you will not have violation at all. But if you are doing snapshot isolation, this thing could happen. It means that snapshot isolation doesn't really necessarily enforce serializability. So this is very interesting, right? So it's still active research. Actually, if you look at existing research in 2012, there's actually a paper about how to make snapshot isolation serializable, right? So I think in the current PostgreSQL, it is actually doing this type of things, okay? So it's doing a slightly more complex version of snapshot isolation as the one that we are talking about right now. We are talking about a very old version of what PostgreSQL was trying to do. So I think starting 9.1, I mean, it's kind of different. Yeah. So this is about transaction and concurrency control, right? So again, it's a huge area, and there's a whole book about it. And we could have a whole course just by talking about transaction concurrency control, right? Which is not the thing we are going to do. So now we understand isolation. Okay, so that's all for today. Starting from Wednesday, we are going to talk about durability, atomicity. We are going to talk about when there's failure in your database, how would you recover it? Okay, yeah, so that's all for today. If you have any questions, I'll be here to answer them. Otherwise, I will see you guys on Wednesday. Thank you.
I actually have a question.
Yeah, go ahead.
Good morning. On Moodle, we have I think, a very interesting question, and it's actually my question as well, but it haven't been answered yet. Was written on the 9th of May, and it's about lecture 13, slide 24.
13, yeah, sorry, give me a minute. 13, 24. Normal form. Okay.
Yep.
And let me open up the slides.
Should I share my, okay, yeah, I see you.
24, right? Okay.
All right, the last two sentences, not language. I forget this word, multi-constraint or something like that. The double arrow to personal number.
Yeah.
As stated on the forum, we cannot prove this because if we set T2 transaction T3 equal to T2 and T4 equal to T1, then we're gonna have like trivial case. We cannot prove in this case just with this data that it's correct. What is written here?
I'm not sure I understand the question. So okay, so this means that in this table clearly there's no MVD from language to person number, right?
Would you please tell me? Would you please show me why is it not possible? Because
okay. Yeah, sorry, I kind of need to context switch and to remember. Yeah, sorry. Okay.
So if I'm not mistaken, now we have language Greek, and then personal number 3002. In this case, this is one case which we are gonna have like the swapped properties of C and Pascal. But if only we see T3 as T2, then they are gonna be like the same. Like this is a really trivial case.
Okay, so let's rearrange this one into this, right? So our language, our person number, we have programming, right? And then we try to so our task is try to reason about language, the MAD between language to personal number, right? So this is our task. So let's try to find two tuples. For example, you have T1. Oh, sorry. So then T1 is, let's say, language is Greek. Okay. And my personal number is, for example, 3. Oh, no, Greek is a very bad one.
Yeah, you see what I mean.
Ah, I see your point, actually. Now I see your point.
I know it's in general case is correct, but it's not in this.
I see your point. Okay. I see your point. Okay, that's a very good point. That's a very, very good point.
Why someone posted it on Moodle and I just saw it, and then I would like to ask you because no one answered this question.
Yeah, sorry. Yeah, so let me yeah, so give me a minute. Yeah, let me think. Yeah, I'm trying to enumerate all the pairs now, so give me a minute. I'm not that fast. Yeah, you're right. I think for this one, yes. I mean, okay. So I know your question. So I tend to agree with you.
Mm-hmm.
I haven't enumerated all the pairs yet, but I tend to agree with you. For example, if this German is Greek, you'll see why that doesn't hold, right?
Yeah, I just wanted to.
Right, all this Ida is Pascal, it also doesn't hold, right? But I think for this case, it's not really clear whether we can say this. Okay. Makes sense. Okay.
In general, yep.
Will this fix your problem?
Yes.
Perfect. Yeah, sorry about this. Yeah. So like we keep using this example, but I never done the exercise of enumerating all the pair to see whether this really hold, because clearly in general it doesn't really hold, right? Yeah.
Okay. Yeah. Thank you very much.
Okay. Thank you for this. Yeah. It's a nice catch. Yeah.
Have a nice afternoon.
You too. Bye. Okay, so if no other questions, I'll see you guys on Wednesday. Yeah.